Oh, welcome, welcome, welcome. Let's grab a few things here. Sorry, this has gotten long. It's hard to look at everything I'm trying to. I'm literally clicked on it. I'm like, where is it? No, there it is. Here are the usual links to the attendance and tutoring. Also, just a reminder, I have an office hour this afternoon from 2:30 to 3:30, so you're welcome to stop on by if you have questions you would like to get help with. Today is the day we focus on the whitener material. So you guys have been talking about confidence intervals. I figured we could go over some of that, kind of when you use Z versus T, and how they calculate them in general and what they mean. Because I'm talking to Sarah, who's helping students in Stats 100, we were talking about how it's really important to kind of have an idea, not just how they calculate a confidence interval and later on how to do a hypothesis test, to actually have an understanding of the meaning behind that process. So I will definitely, when we do some of those today, talk about what they mean. My cat has been sitting on my lap occasionally, and she really, my keyboard is really kind of dirty looking. She likes to, sorry, I'm gonna place it in I wonder why, like I never hit that button. Why is it so dirty there? It's weird. Anyway, not vital or important, but just also, it was really quiet in my office until like a minute ago, and then they started doing more work, which I think is going to stop soon because I think they're just moving big pavers back and forth. They can't carry them, so hopefully the noise abates. So confidence intervals, I think, is where we should start. And there's a couple different examples that I had. So really, I mean, I think the textbook has a lot of good examples. So let's look at this one. So I'm just grabbing some problems from the textbook. And then I've also got some bigger sample stuff to look at as well. If you have specific questions you want to ask, you're of course always welcome to. And I'm just going to start doing some examples. But again, feel free to chime in if you have certain things you would like to see. So here's what I have got. Let's see, where'd you go? So here's, I'm not going to write the whole thing, lengthy, but here's the setup. Healthcare workers who use latex gloves with glove powder on a daily basis are particularly susceptible to developing a latex allergy. Symptoms of a latex allergy include conjunctivitis, hand stuff, right? Okay. Each in a sample of 46 hospital employees, so N is 46, I think. Actually, let's hold off on that. Who are diagnosed with latex allergy based on a skin prick test reported on their exposure to latex gloves. So we are looking at 46 people that have a latex allergy. Oh, sure, I can look at the problem. Yeah, I can look at the problem number 2 that I did on the quiz I gave. Sure, I'm happy to. Let me actually, I don't remember. I know I wrote it like yesterday. I don't remember what it is. Let me take a look real quick. Let me continue with this problem, and then I'll definitely come back to the quiz. Let's see. Oh yeah, we can definitely talk about it. Yeah, for sure. I definitely intend to talk about problems like that as well. So here's what we've got. We have, so N equals 46, and the number of latex gloves used per week for this sample of 46 people was a sample average of 19.3 latex glove uses per week, and a sample standard deviation of 11.9. Okay, so from this data, we are going to try to construct a 95% confidence interval for the average number of latex gloves gloves, sorry, the words here, used per week by the workers with a latex allergy. Okay, so, and actually before we even do that, well, no, that's fine. So the way we're going to construct this confidence interval is the usual way. And well, I should back off on that because there are different usual ways depending on the information you've got. In this case, we don't really know about the distribution, and we don't know if it's normally distributed or not. We also don't know what the standard deviation is, but our n is large enough that it's still okay to use the regular z-score kind of method, right? N is bigger than 30, so we're kind of fine. Like even if we don't know how it's distributed or what the standard deviation is, right? Because these are sample statistics, not population statistics. So since our n is large enough, it is okay to go ahead and use the usual z-score. So here's how we're going to calculate it. We're going to calculate our confidence interval as our sample mean plus or minus our z-score for 95%, which maybe I'm not writing that the usual way. I'll change that in a minute. Times our sample standard deviation divided by the square root of our sample size. This is the usual way of calculating this, at least in my mind, the usual way. Where the Z 95% score is just, and I feel like I've probably written that wrong. Right, that's the Z score where I'm sure, I feel like I need to fix that, right? Where 95% of the data is in there. So it's probably on the table from Dari's class. It's probably actually looking for 47.5%, right? Because in the table from Dari's class, it's so loud. I was like, oh, it's nice and quiet, and then they started like, right, this class is starting, right? For the table that Dari's class has, right, the area in there is half of the area, so that's 0.475. Often it's written as Z alpha over 2, I think, where alpha is some amount like out here. Anyway, hopefully you've seen this particular number enough times to know it's 1.96. So if we look at the Z table, the Z score of 1.96 has exactly 47.5%, 1.475, 0 in that section there, and then there's the same amount over here. So you're getting exactly 95% in there. So here's how we're going to calculate this confidence interval. It's going to be x bar, so 19.3 plus or minus 1.96 times our sample standard deviation, which is 1.9, divided by the square root of 46. And again, a reminder. The reason why you're not just using the standard deviation, if you're using the standard deviation divided by the square root of the sample size, is because when we're talking about how the mean is distributed, right, it's not distributed as variably as the actual data points. Right, the mean, if you took a bunch of, if you took a sample of 46 and another sample of 46, and another sample of 46, you took the averages of all those, the average of those are not going to be nearly as spread out. So the standard deviation is smaller because of that. And it's all about the central limit theorem. The central limit theorem says that the distribution of the means is much more centrally distributed. So that's why you're getting to divide by this, and you get a much tighter interval than you would otherwise. And the rest of this is just arithmetic. So let's do the calculations real quick. So let's see here. I got 1.9 divided by the square root of 46, which is 1.75-ish. Multiply that by 1.96, and you get 3.44-ish, and then you 19.3 plus that to get 22.7 for, let's say, as the, actually let's look at the book, because the book has the answers in it. Oh, they're just the, so here's how they wrote it in the book. They wrote it as 19.3 plus or minus 3.44. And you could do, right, you could do more with that. You could say, well, that's going to be, you could do an interval from, let's see, 19.3 plus 3.44 is 22.74. And 19.3 minus 3.344 is going to be 1615.86, I think. Okay, so great, we can do the arithmetic. But I think the more important part here is being able to explain what this means. And they definitely ask that in the next question in this book. So the next question is, or do you give a practical interpretation of the interval you found? So what does this interval mean? Well, so it's a 95% confidence interval. So that means there's a 95% chance that the actual average number of, what were we measuring? Time similar latex. So I have to be more careful about that measure. The average number of times a person with a latex allergy or a healthcare worker with a latex allergy wore latex gloves during a week is between 15.86 and 22.74. So that's what we're saying. There's a lot of words to say here. So we are 95% confident that the actual average number of times one of these people wears latex gloves per week is between 15 and 22, or rounding, 15.86 and 22.74. So that's what this means. And but so that's kind of what I want you to take away from that. Let's look at another example like this. So this example is actually from the OLI textbook, and I was looking at page. Sorry, where my notes went here. I was looking at page, I think 208 on your textbook, where, so actually let me share my screen. Let me minimize something before I start sharing my screen. Just not too much in the way here. Yeah. Gosh. All right, so I'm over here looking at page 208. So the person, so here's what we have, background. Some studies suggest that women having their first baby at age 35 or older are at an increased risk of having a baby with a low birth weight. A medical researcher wanted to estimate the mean weight of newborns who are the first child over the age of 35. To this end, the researcher chose a random sample of 125 women, ages 35 and older, who were pregnant with their first child and followed them through the pregnancy. The data file, which I have over here, contains the birth weight in grams of the 125 newborns. Okay. From past research, it is assumed that the weight of newborns is a standard deviation. So in this case, we know, or we think we know, the population standard deviation is 500 grams. We're going to estimate the population mean is a 99% confidence interval. All right, so here's all the data. And right, so we're starting up here, birth weight 3,870 grams, all the way down to the last one here, which is 3,080 grams. For those of you just joining us, we are looking at this problem from the OLI textbook, and I wanted to. I always forget where. Sorry, I'm always like weirdly trying to do things here. And here is the attendance again. So there's actually this explains a different way, a way you can like just use Excel to do it, and we can definitely do that at the end. But I kind of want to talk about the process because I think it's important. So to get the average, I typed in average, right, or equals average, and then parentheses the first entry, which is in what do you call the little boxes in Excel? Boxes? I feel like there's a better name, which is in this little box, A2, colon, all the way down to A126, right? So that's what I've got, A2 to A126. I feel like there's a different name for the boxes in Excel that I should know. Anyway, so we found the average. So that is, so for this problem, we have right off the bat, and our sample average, X bar. Sorry, I hope you guys can see this. I'll go back to this. Our X bar, that's not the kind I wanted. X bar is 3,111.36 grams. And although I don't think we need it, I did calculate the sample variance by just doing, so I wasn't sure what the command was. So what I really did was I started typing in variance. And so I did VAR, and then I chose .s for sample. And then I did the same A2 colon A126, take the variance of all those. Now in this case, we don't actually, oops, yeah, that's fine. And then I did the square root of that in the next pane. Maybe pane is the right word I'm looking for. Excuse me, to get the sample standard deviation. Now, I think that was actually not necessary because they tell us right here that the sample or the actual standard deviation is 500 grams, which is very close to the sample we got to. Good. In fact, if we'd done the population variance, we might have gotten close to 500. So then we can calculate the confidence interval, a 99% confidence interval, in the following way. These are our confidence interval. It's going to be X bar plus or minus, and let me see how to do it. Yeah, okay. So we want a Z, I'm going to do Z alpha over 2 because I feel like that's pretty standard, times our actual standard deviation. If you have the actual standard deviation, you should use that, divided by the square root of n. So it's perfectly fine to use the sample standard deviation if your sample size is large enough, right? That's the case where the standard deviation is unknown. But if it's not, then we have to do something different, where we have to use a t-square, I believe. So in this case, we're going to get 3,111.36 plus or minus. Now the z-score here, right, again, this is a 99% confidence interval. So we're looking for the place, the z-score, where, right, 99% of the data is in here, which means 1% is over here. So this is, my alpha is 1% or 0.01. Alpha over 2 is 0.005, which is what is right there, right? That's 0.005. So I'm looking for the z-score, and again, I can use z because my n is large enough, with 0.005. So I'm going to look at my z table. All right, let's go over the z table here. So looking at my z table, I'm looking for the place where the area to the left. Well, again, so this is the z table that I'm looking at here, where it's all the area to the left, right? It's not just to the midpoint; it's all the way to the left. So I'm looking for 1 minus 0.005, which is 0.9950. So I'm looking for the place where the area is 0.9950. So let's see. Where am I here? 99995, So, oh yeah, so it's right between these two, which I believe is 2.575. That looks right to me. So I believe our z-score is 2.575, right? We're splitting the difference between 2.57 and 2.58 times 500 over the square root of 125. So let me stop sharing my screen for a sec just so you guys can see this better. Right, so that's what we should be getting. Oh, sorry, I'm in the way. My head does not see through. So we're getting our sample average plus or minus the z-score for a 99% confidence interval times our actual standard deviation divided by the square root of our sample size. So I'm calculating this, and hopefully I end up getting the same thing that they got. I end up with, let's see here. So the way I calculate this, I usually do this part times this part first. So 500 divided by the second square root of 125 is 44.7-ish. times 2.575 is 115-ish. So I'm getting 3,111.36 plus or minus 115 point, I'm gonna round that to 1.6. So let's see, 3,111.36 minus 115.6, sorry, is 2,996.2 to 300, you know the numbers, plus 115.16 is giving me 3,226.52. So we can say with 99% confidence that the true average weight of a baby born to a mother who gave birth after age of 35, we're 99% confidence that that baby weight is between 2,996.2 grams and 3,226.52 grams. Which would mean, as far as the context of this question goes, if we look back at the question, let me share my screen again. So we look back at the question here. Oh, good. Look, so I'm happy that my numbers did turn out to be essentially the same as what they're a tiny bit different, right? I'm off. They did one more decimal place than I did, or they rounded maybe slightly different. Close enough. Sorry. No, they're just trying to estimate. I thought they were trying to answer some question about like, is the baby underweight or not? From this data, you probably couldn't argue either way that you know that the 99% confidence that the baby is underweight or not, because some of the interval contains the weights less than 3,000 and some of it doesn't. We can talk more about that later when we talk about hypothesis testing. There was something else I want to say. Oh, the other thing I want to say is you totally could do the other thing here where we just use this cool Excel function, confidence.norm.asn, where A is the 1 minus your confidence level, N is or S is the sample or the actual standard deviation, and N is the sample size. So if we just throw that in there, I mean, it feels kind of dumb to just write it here, but let's do it anyway. I feel like I'm about to do something stupid. Oh no, I'm just, oh, I see. They're using that to calculate. So they're using that to calculate this 115 value that I got. So we do, so right, instead of having to look up the z-score and then multiplying it by the standard deviation divided by the square root of the sample size, they just do that all in one pool. Ooh, that's big. So why didn't that work? Because I forgot my equal sign. Ooh, and because it's all in like, let's try that again. Let's undo that. So let's type in equals confidence from dot norm. Are they trying to give it to me? There it is right there, right? And then we need the alpha, which is 0.01. We need the standard deviation, which is going to be 500, and we need the size. That's kind of convenient. So there it is, exactly. And then we just do our value, 3,111 minus that to 3,111 plus that. All right. Yeah, I think that's a fairly decent example. Kind of like that. So there were questions about the quiz, and let's go ahead and look at some other examples. Or we can just look at a similar example using different numbers. And so I think probably for population proportions, actually, you know what I should do is I should look at what she's got. So going to, I'm still sharing my screen, which is perfectly fine. Let's look over here. So I know that I look here, I want to go to confidence intervals for population proportion. So we look at this. There are a couple things to know about how to calculate this. So one, So we have and so just for some notation stuff, here's what we have. The population proportion I should actually make sure I'm saying this right. I believe we just label it as P, and the sample proportion is given by P hat. The standard deviation for the population is given by sigma still, and the sample standard deviation is given by S, and it's calculated as, let me make sure I got this right. No, it's okay. It's the square root of, let me turn this right. Yeah, it's the square root of P times 1 minus P over N. And yeah, so what we usually do, since we don't usually know the true population proportion, is instead we use the square root of P hat times 1 minus P hat. So I imagine that's probably where some of you, at least if you're looking at the quiz, are running into kind of a roadblock, is how you're supposed to calculate that part. That is how you calculate the standard deviation of a proportion. Now, looking at this here, sorry, I know I'm up super close. So let's read through this example she's got that the book has on page 212. Share my screen with you guys. I know, I imagine some of you might have already read it, but it's all right. So you get to listen to my lovely voice. Drug Viagra became available in the US in 1998. Interesting. In the wake of an advertising campaign was unprecedented in scope and intensity. Yeah, I definitely remember those Viagra ads back in 1998, before I imagine most of you were born. Okay, anyway, not important. A Gallup poll found that by the end of the first week in May, 643 out of a random sample of 1,500 adults were aware that Viagra was an impotency medication. So that's like about 60% or 64%. I think it just made it 1,000 instead of 1,005. So let's estimate the proportion P of all adults in the US who, by the end of the first week of May, were already aware of Viagra and its purpose by setting up a 95% confidence interval. So first we calculate the sample proportion P hat. And again, P hat is just, literally I just said it, it's the sample proportion. It's just the number of things that we have out of the total number. So 643 out of 1,005 is approximately 0.64. It's probably not exactly 0.6. So there's definitely some rounding happening here. Let's double check. Yeah, it's 0.639800995, et cetera, et cetera, et cetera. So a 95% confidence interval for P is P hat plus or minus. Now I don't know where this 2, oh, I know where this 2 is coming from. Do I know where this 2 is coming from? I don't know about this 2. Well, let's continue on. So we get P hat plus or minus 2 times this here, which is just our sample standard deviation. Why are they using 2 and not 1.96? That's a good question. Let's go look back at the previous page, because so if I were doing a 95% confidence interval, I would feel like the number should be 1.96. If you guys have opinions or thoughts as to why it isn't, I would be happy to hear them, because to my mind, I feel like it should be 1.96. So let's look back at the previous page and see what we can find. So we get 2 plus, so P plus minus. So plus or minus the margin of error. So the margin of error is the confidence multiplier times the standard deviation. Okay. Sorry. So the standard deviation is just that. Oh. So since like the sampling distribution of X bar, the sampling distribution of P hat is normal, the confidence multipliers that we use in the confidence interval P will be the same Z star multiplier we use for the confidence interval U, and sigma is known. using exactly the same reasoning. The multipliers we'll use are 1.6452, 2.576. And that's probably what I should have been using in the previous problem instead of 2.575, 2.576. 2 here makes me that I don't love that. I don't know why that's 2 and not 1.96. That bothers me. Let's look further back. So let's go back to the beginning of this, because I'm wondering why they're able to say 2 there and not 1.96. Huh. I don't have a good answer. Wow, that really bothers me. Sorry, you guys. I feel like, I really strongly feel like it's supposed to be 1.96. I don't know why we are making this, why we're just rounding it up to 2. Bummer. I'm guessing nobody has a good idea why that is true, because I sure don't. But it definitely feels like, let's look around. It just feels, I don't know. So I'm sorry for getting stuck on this, but it just feels like there must be a real reason for doing that, because otherwise it's just laziness. And I don't feel like it's just laziness. Like, it seems like there's an actual reason to pick 2 instead of 1.96. And I unfortunately do not have a good answer as to why that would be the case. I'm going to look at my z table again just to be sure. Looking at my z table, I look at the score for 2, and yeah, I'm getting 0.4772, but I want 0.475, which is definitely back exactly at 1.96. So if you guys have the opportunity, I would maybe ask your instructor, Professor Whitener, about why they're using 2 there instead of 1.96, because I do not have a good rationale for why they're doing that. I wish that this confidence interval about P here, I wish they referenced them, because they talk about, so if we look at this here, right, the multipliers we use are these for that. Yeah. They talk about those multipliers, and I know that they're saying to do that for the other ones, but it doesn't seem to be clear where that's coming from. All right, let's look through real quick. Hopefully you guys are finding this somewhat valuable. I just feel like there's got to be a good reason for this, and I would want to know what. Well, obviously I would want to know. Talking about that. I don't have to scroll back up. There's a way I can go down. Okay, yeah, we talked about the z-score there. Okay. All right, I guess they're just, yeah, they're saying it right here. There's a 95% chance that the sampling we get falls within 2 standard deviations of the mean. That's disappointing. That feels lazy to me. Maybe I'm wrong. Maybe there's something else happening there, but I would want to use 1.96. So I would ask your instructor about that, because it seems like it should be a different number unless there is some specific reason that they want to use 2 instead. But yeah, that's, I found it disappointing. All right, back to the problem we were looking at. Sorry, I got real caught up on that. So if we look back at the next page here. So the way they calculated this was they just did, your sample standard deviation, sorry, your sample portion, p hat, which is 0.64, plus or minus your z-score, which I guess is 2. Seems like garbage. Sorry, my opinion is that it's garbage. Times the sample standard deviation, which is calculated as the square root of 0.64 minus 0.64 divided by 1005. So what we're saying there, and again, so regardless of why the numbers may or may not be, I mean, I know the 1.96 probably wouldn't change it that much because we're only going to the second decimal place here. The thing that's important with a lot of statistics is actually being able to interpret the mean. So regardless if the numbers are right, I think they're wrong. We can say with 95% confidence that the actual proportion of people in the United States that were aware of Viagra being a drug and how it worked was between 61% and 67%. Okay, that is something meaningful. I never like doing these ones. So, I mean, it's good to do these. I always feel like I have to read so much to do these ones. So let's say, did I get this based on the answer? Okay, fine. Yeah. So, okay, look, this is actually, that's not really feel better about their choice. So 95% confidence interval P is given by this typical formula, P hat plus or minus Z star times the thing we just calculated. If you're taking my quiz, I would encourage you to use 1.96 for 95% confidence interval or whatever. And then they do some, interesting. So then you can use this, which I guess here is why 2 might be nicer than 1.96, to isolate n in this expression to figure out how large a sample size you need to get a margin of error that is whatever level you want it to be. So if you want the margin of error to be like, 0.05 or 5%, you can set n equal to 0.05. P hat is what you calculate it to be, and you can solve for n to do that. So that's kind of useful. Oh, and then they do, that's smart. Sorry, I feel like I'm just kind of reading through this and looking at it like, oh yeah, that's a good idea. So what they do with this then is they try to maximize this. And the way that it's maximized is when P hat is equal to 1/2. So they throw in the 1/2, they get 4 times 1/2 times 1 minus 1/2, which is just 1 over m squared. So you can maximize this value. You can find the biggest that it has to be based on the margin error you want by just doing 1 divided by your margin of error squared. So that's not unuseful. Yeah, I kind of like that. I'm sure I knew that once upon a time. All right, so let's see. Let me stop sharing because I feel like I'm just kind of fiddling around here. What else? So, I know what I want to say. I had an example. So something to be aware of is that, where'd that page go? I had it. Darn it, I knew I was. Let me see here. There was something I wanted to mention to you guys that is actually, yeah, okay, here we go. Let me share my screen. So I thought this was actually pretty important. So when is it safe to use the confidence interval we develop? So these are the times we use it. If you know you have a normal distribution, sorry. Yeah, so if we know that the variable is distributed normally, then that's perfectly fine. You can totally use confidence interval with the z-score as you would. Or if you know your sample size is large enough, right? And I think our usual rule of thumb is n is greater than 30 for a population. So it is n is greater than 30, but it's a different rule for the proportion, which I'll get to in a second. The only time you can't just do this is if we have a small sample size and we don't know that the population is normally distributed. In that case, that is when you have to use the t-score instead of the z-score. So let's look at this did I get this section, because I think it's valuable here. Situation A. So here are 4 situations in which a confidence interval is called for. And they're asking which one can we not use the confidence interval that we developed. So situation A. In order to estimate mu, the mean of high school, oh my God, the mean salary of high school teachers in a certain state, a random sample of 150 teachers was chosen. So already we have a large sample size, we're good to go. Situation A is fine. I don't even need to read the rest. Yeah. But here it's also, right, the standard deviation is also known. So we kind of, here we're in the best situation where we know standard deviation, we know sample size, we're good. Situation B, medical researcher wanted to estimate the mean for the mean recovery time for open heart surgeries. Researcher followed so next 15 male patients, so n equals 15, so that's small in the age group underwent open heart surgery in his medical institute. Even though the sample was not strictly random, there's no reason to limit the sample to the next 50 patients to introduce any bias. Okay. The mean recovery time of the 15 patients was 26 days. And the large body of research that was done in this area is assumed the recovery time for open heart surgery have a standard deviation of 3 days. So again, even though we have a small sample size, we're in that the variable varies normally. We know how things work here, so that situation would also be fine. Let's look at C. In order to estimate the mean score on a quantitative reasoning part of the GRE, a random sample of 1,200 students. So again, we're in the large sample size situation, so we're perfectly fine. We can use the confidence interval. And it is known that this quantitative reasoning scores vary normally with a standard deviation of 150. Oh, I think I made a mistake for part B, but we'll correct that in a second. So situation D, we have a mean, we want to estimate a mean, we have a random sample of 12, and their times recorded. The average time, 7.5 minutes. From past experience with similar tasks, the time is known to vary normally with a standard deviation of 1.3 minutes. Okay, so I know it's either B or C that we can't use, and I know I discounted D earlier. Well, let's go back and talk about why it actually is B. So in D, they talk about, so both B and D have a small sample size, right? So we're in this column. D says, from past experience, the time is known to vary normally with a standard deviation of 1.3 minutes. Whereas in B, which I misread earlier, is assumed that the recovery times have a standard deviation of 3 days. But it's not saying it's assumed to be a normal distribution. So B is actually the variable where we can't use a confidence interval in this usual way, because we have a small sample size and we don't know that the variable is normally distributed. So let's check if B is right. Cross my fingers. Yeah. So let's see what they say. Even though the sample was selected in a manner that is not strictly random, no bias is expected. However, the sample size is small to require that the recovery times are normally distributed. Since we don't know that, we can't use the confidence interval. So in that case, instead of using the confidence interval generated using a z-score, you have to use a confidence interval with a t-score, which ends up using a larger value. So you have, right, you have to have a bigger confidence interval to be actually confident that you have the true population. So I know that was a lot of talking. Hopefully that made some sense. Certainly if you guys have questions, feel free to pipe in. So I feel like this next question is the same sort of thing. I don't think we need to have me read through that all again. I could, but I think that's super valuable. But then we talk about down here, if your standard deviation is unknown, we have the following. When variables have been well researched in different populations, it is reasonable to assume that the population standard deviation is known. However, this is rarely the case. If sigma is unknown, the good news is we can easily replace the population standard deviation with the sample standard deviation. So most of the time, it's not a big deal. So in fact, and that was what I was starting to do with this, all this data over here, right? I was going to use this 501 before I realized that they actually told us that the population standard deviation was 500. So usually you can just sub in the sample standard deviation to the population and you're fine. Bad news is, once sigma has been replaced by this population standard deviation S, we lose the central limit theorem. together with the normality of the sample mean. And therefore, the confidence multipliers z star for different levels are generally not accurate anymore. The new multipliers come from a different distribution called the t distribution, and thereby denoted by t star instead of z star. So the confidence, so notice they haven't said anything about the largeness yet. We'll get to it in a second. So the confidence interval ends up being x bar plus or minus the t-score times the same sample standard deviation. Now, yeah, I mean, so important difference. The new multipliers t star have the added complexity that they depend on both the level of confidence and on the sample size. For example, the t star used in the 95% confidence interval when n is 10 is different. And we talked about that last week. I think how the n minus 1 is the degrees of freedom, and you have to use that to find the appropriate t-score. But there was something here that I wanted to mention that I thought was on this page. So what I want to point out is that while you do have to use the t-score when you don't know the population standard deviation, if your sample size is large enough, your t-score ends up being essentially your z-score anyway. And I thought that was on this page. Oh, there it is, final comment. It turns out that for large values of n, the t-star multipliers are not that different from the z-star multipliers. And therefore, using the formula x bar plus or minus, like the usual formula for mu and sigma is unknown, provides a pretty good approximation. When n is large enough, how large? Bigger than or equal to 30. Okay, I feel like I'm just kind of talking at you guys. Not that there's anything wrong with that, but would anyone like to, is there anything else I should be saying in the last few minutes here that you guys would like to hear about? It's like, no, please just shut up. I'm kidding. I don't think you're really thinking about it. Yeah. So I think the hard part about this, good. I think the hard part about confidence intervals in general are twofold. Maybe three. Thing one, you have to know when you're using a t-score versus a z-score. And I think that little table that we were just on a second ago. Where'd you go, little table? Sorry, one sec. I think this little table really kind of covers it fairly. Oh, I know what I want to say. So this little table, I think, covers it pretty well, right? You can use the z-score as long as you have a large sample, or we know that the population varies normally. But when you have a small sample, n less than 30, and we don't know that the population varies normally, that's when you're kind of stuck, and you have to use a t-score, and that's when you have to look at the degrees of freedom. The other thing that I think is the thing that's probably the most important is how to interpret the confidence interval, right? So when you're finding a confidence interval, you're saying, I know with usually 95% confidence is the value we often use, although there's lots of points, that the actual population mean is within these two values. Now, the other thing is for population proportions, there is a slight difference in the requirements. I don't know if they actually talk about it here. I know it's in the other textbook. No, I want to say, sorry, I feel like it should be in there, and I would like to actually show it to you in the text, but it's not. I mean, it's weird if he's saying it. So there's usually the rule of thumb for, here it is, I found it, this. So right here. So the rule of thumb is that it's perfectly safe to use a z-score for a population proportion when n times p hat is bigger than or equal to 10 and n times 1 minus p hat is also bigger than or equal to 10. So that is, when that is true, then we're saying we know that our n is big enough that we can use the z-score. I don't think they talk about what you do otherwise here. Although I know that there's something in the other textbook that's kind of funky. Usually, I feel like usually the alternative to if you haven't met this condition here is typically not really discussed. But I'll look into that and see if I can find anything more about that. So next time, meaning, I mean, we might talk about this on Thursday with Nimdari folks, if that is what they want to talk about. But next week, I imagine we will talk about some hypothesis testing and how that kind of works. And there's definitely a lot to say about hypothesis testing. But the general idea here is that often people for hypothesis testing liken it to how the US legal system is supposed to work, right? That we are generally, so typically people say the null hypothesis, right, is the idea that someone is innocent until proven guilty, right? So we are starting with a base assumption of not guilty. That's our null hypothesis. And to reject the null hypothesis, we have to find sufficient evidence to do so. Just like to find someone guilty, you have to find sufficient evidence to do so. So, right, when they're reading the vertex, it's not innocent vertex. When they're reading the verdict, it's not innocent or guilty, it's not guilty or guilty. So we're saying guilty, we found enough evidence to reject the assumption of not guilt, or not guilty, we did not find enough evidence, right? We're not saying someone's innocent necessarily. We're just saying that we don't have enough evidence to show that they are, in fact, guilty. So that's kind of the idea that I want you to sit with. That's definitely how I imagine hypothesis testing in my mind. Either we have enough evidence at a certain confidence level to say, oh yeah, we're gonna reject our base assumption here, or null assumption, and go ahead and say, yeah, we think this other thing is true, or we didn't have enough evidence to reject it. So we're not gonna say we think the original thing is true. We're actually just gonna say, I don't have enough evidence to say it's not true, which feels like a lot of words, but yeah. Okay, that's all I've got for you guys today. Hopefully you found that valuable, and I will see you all on Thursday if you want to be here, on Tuesday if you don't, and office hours this afternoon if you guys got questions. I'll see you then. Bye.